Hello, good evening.
Good evening, ma'am.
Yeah. So today we are here to discuss the 11th live session of the
Yeah.
NPTEL course Symmetry and Group Theory, taken by Professor Anindya Datta from IIT Bombay, and I'm Shruti, PhD scholar in the same department. Okay, so let's start. So today we are discussing the assignment number 10th, and next week, which is going to be the last live session officially, we will be discussing assignment 11, but I'm going to take one extra live session. uh, you will get notified about the date, exact date and time, and in that I'll discuss the last 12th week assignment. Okay.
Okay.
Yeah. So did you solve this week's submitted?
Yes, ma'am. Yes, submitted.
Okay, all correct.
No, ma'am. Only 3 and 5 is correct.
Only 3 and 5 correct.
Yes, ma'am.
Okay. Okay, yeah. 3 and 5 are easy. Sixth, you did not get sixth.
No, ma'am.
Okay, let's start from the easiest one. Okay, you did not get sixth, so let's start from sixth. So, okay. So this one we have discussed actually. It says that for the same character table in the question number 5. So in question number 5, we have C2V point group. Okay. So here also we have to use the C2V point group. So it says that if the initial and final states belong to A1 and B1 irreducible representation, so the allowed electronic transition from A1 to B1 is uh, accompanied by which polarization of light. Okay. So what in these type of questions, what we need to find actually, from A1 to B1, we need to find the direct product. Okay. A1 cross B1. Okay. So what are the characters of A1? Let's write A1 first. So we have all 1. It is totally symmetric representation, right? And then B1. B1 is this. Okay. You if you would have used this character table, you could have get this question. We have discussed this in earlier sessions. 1 minus 1, 1 minus 1. Okay. So cross multiplication means you have to multiply character wise. So 1 multiplied by 1 is 1. This is minus 1. This is 1. And this is minus 1. So now this becomes which representation? Which representation is this out of these 4?
B1.
This is same B1, right? Because you are multiplying it with all 1, it won't change. So
Yeah.
it's like multiplying any number by 1. If you will multiply 10 by 1, you will get the answer 10 only, right? So this is the same thing. You are multiplying B1 with the totally symmetric representation, so it will not change. So it will be B1 only. Also, one more thing, if you multiply any two representation with itself, you will get A1. Okay. For example, B2 into B2, you will get A1. A2 into A2, A1. Like that. Okay.
Okay.
So now we have got this B1. Now B1 is associated with which polarization? We have to see the linear terms, okay? The 1 degree terms like X, Y, and
Yeah.
Z. So it is associated with X. X gets
Okay.
transformed according to B1. So the answer to this question is X polarized. Okay.
Okay.
So this is the correct answer. You get it now?
Yes, ma'am.
Yeah, we have discussed this na in some earlier sessions. There were so many questions like this.
Mm, Yes.
Yeah. Okay, so when you are not getting any question, you try to look back the previous assignment. You may find some
Sure.
hint. Yeah.
Okay, ma'am. Yeah.
Okay. So let's move to the fifth one. This is again the C2V point group related question, and it is asking that the reducible representation corresponding to three translational degrees of freedom tau r. Now we have to see the degrees of freedom for the basis set x, y, and z. Okay, so we have see in the C2V point group we have E, C2, sigma V, sigma V, YZ. Okay, this is XZ. Now for X, what we have this one, or you can simply write Z first because Z is first. Z is totally symmetric. Here is Z, here is X, here is Y. So for Z we will have totally symmetric all 1. Okay. Now for X, what shall I write here? X gets transformed. For E it will be both 1 because under identity nothing changes. Now under C2 x becomes minus x, so it will be minus 1. This is 1, this is minus 1. This is molecular plane. Now for y, this y gets transformed according to B2. So this is minus 1, this is minus 1, this is 1. Okay. So we need to find tau translational. Translational means all three components x plus y plus z. Okay. So what we can do, we can just sum these. Tau translational will be equal to, okay, you have to just sum the characters of xyz basis under each operation. So this will be 1 plus 1 plus 1, 3, 1 plus minus 1 plus minus 1. So it will be minus 1. 1 plus 1, 2 minus 1 will be 1. 1 minus 1 plus 1. So this will be plus 1. Okay. So the answer is B. Okay.
Okay.
And the what could be the reverse question? The reverse question could be, you have to, this is tau translational. Now you have to break it in terms of irreducible representation. Okay. This is a reducible representation, right?
Yeah.
So when you will break it into irreducible representations or the linear combination of irreducible representations, what should you get? So you have summed this, right? Yes. So
Yeah.
this is from A1, this is from B1, and this is from B2. So when you will break this using that formula, the great orthogonality theorem formula, you will get these same components. So if you try, break it, and you will get these three components only.
Okay.
How do we break that?
Mm,
What is the formula? Do you recall what is the formula which we use to break these reducible representation into irreducible?
China.
No, AI is equals to 1 upon h. This formula I'm asking.
Okay.
So this formula, when I say that you have to break a reducible representation, this is a
Okay.
reducible representation, into irreducible representation, we use this formula. This comes from great orthogonality theorem.
Yes, ma'am.
Great orthogonality theorem. So what is h here?
It's 4.
Yes. So h is order equal to 4. So let's try. Now first is a1. Okay, a1. So a of a1 should be 1 upon 4. Now can you do this?
Yes, ma'am.
1, 1, 3.
3.
Can you do this and tell
Yes,
me
ma'am.
the answer?
Yeah. One.
Yes, it has to come 1. So plus so on, it will be equal to 1.
Yes, ma'am.
Now check a of a2.
Please give a character table of it, C2.
Yeah, sure.
One, minus 1, minus 1. Got 0 है.
0, right?
Yeah.
क्योंकि यहाँ देखो a1 plus b1 plus b2, we took combinations a1 b1 b2, there is no
There is
a2,
no A2. Yeah.
so it has to come 0 only. So
Yes,
your
ma'am.
calculations are correct. Now you can guess, right, what will be b1 and
Yes,
b2?
yes. Yeah.
What should it be?
1.
1. And b2?
1.
1. So using this reverse calculation also, you are getting the same answer, right, as here,
Yes, ma'am.
because you took
Yeah.
combinations and you did not multiply it. Suppose it was 2 times z, so you have to multiply it with 2, all the characters. Then
Yeah.
a1, then the coefficient of a1 should have come as 2. Okay, but
Yes,
here
ma'am.
we have taken all ones,
Yeah.
so it's all the coefficient came as 1 1 1, and for a2 it is 0, right?
Yes, ma'am.
Okay. fourth question is the point which is not an advantage of using incomplete projection operators over complete projection operators. So uh, the answer to this is slightly confusing for me as well. The answer is first one. The resultant LCAOs are automatically normalized. I don't
Yeah.
know why it is not an advantage, but the answer is this only. But
Yeah.
other things are definitely an advantage, that there is no need to work with the entire transformation matrix.
Yeah.
Suppose we have a point group, suppose D6H. Okay, so here how many operations will be there? E, C6, S3, and C3, C2, sigma V's, sigma H. So many will be there, right? And
Yeah.
suppose, so if we are using projection operator, we have to work out the matrix of all these. Okay,
Yeah.
we have to find out the transformation matrix of all these if we want to use the complete point group, sorry, the complete projection operator. But we don't need to do all this, because what is incomplete projection operator? Incomplete projection operator only cares about the diagonal elements. Okay, the diagonal elements of these transformation matrix. And diagonal elements, the sum of the diagonal elements refer to what? What is the sum of the diagonal elements of a transformation matrix called? It is the character, right? The character or the trace. So if you have a, suppose you have a C2 operation, okay, you will have some okay, 0 minus 1 0 0 0 minus 1. Suppose this is a C2 operation transformation matrix, okay, and the
Yeah.
character will be what? Sum of all these, right?
Yeah.
Sum
Minus
of
one.
diagonal element, character will be minus 1. So
Yeah.
what incomplete projection operator does, it deals with the character only. Okay,
Yeah. Okay.
so the atoms which are unchanged, only that atom contribute. So the atoms which are unchanged comes to the diagonal, right? The atoms which change place will come here, here somewhere of diagonal elements. Okay, so incomplete projection operator works with diagonal elements, so we don't need to calculate this element, this element, this element. Okay, we just need to calculate the diagonal elements, so we don't need to work with the entire transformation matrix. Okay, and also, so if we can work with characters, so where we get the characters from the character table, so we can work with the character table directly. And
Yeah.
yeah, T point is also an advantage because the process is less tedious. We don't have to work out all the elements of all the transformation matrix. We can simply work with characters. So it's a the number of steps involved in these calculation using incomplete operators will be less. So it's an advantage. So only A point seems logical, which is not an advantage. So this is the correct answer. Actually, I think it should be are not automatically normalized, because we have to normalize whatever comes with some coefficients. We have to
Hmm.
normalize. So I think there is some printing error or something with this question is wrong. Answer given is A.
Yes.
Yeah. You okay with this?
Yes, ma'am.
Okay. for third, it is for C2H4. What is C2H4?
Okay.
C2H4? Yes. Okay. So this is the molecule. Shown in figure it is written, but there was no figure given, but this question was discussed in class. Okay. In lectures it is discussed where it is mentioned that C2H4 is this.
Yeah.
Now, okay, so now the a projection operator operates on sigma 1. Now what is sigma 1, sigma 2, sigma 3? Let's write. This is sigma 1. Sigma 1 means the s orbital of hydrogen. Sigma 2, sigma, let's write sigma 3 here and sigma 4. Okay.
Yes, madam.
And let us write the coordinate system also. So this is x-axis, this is y-axis, and excuse me, 1 second. Hello? Yeah, jaldi karo, I'm in class. Okay, so we were here. So this is the coordinate system, x and y, and z is projecting towards you like this out of screen. Okay. So now first thing what we need to do is we need to, before getting started with the projection operator, we need to find the reducible representation associated with these sigmas. Okay. Now the point group for this is what?
D2H.
D2H. Okay. So I am simply writing here. I'll give the whole thing. C2Y, C2X, I, next will be sigma XY, sigma XZ, sigma YZ. Okay. And if I write the reducible representation means tau of these sigmas. Okay. So under now we are considering these sigmas as one entity. This, what is this? Sigmas are oneness orbital of hydrogen. Okay. Now under identity, what will happen to these sigmas?
Yes, madam.
So under identity, nothing will change. So everything, the character will be 1. So sum of the characters will be 4. Under C2Z, all will change place because C2Z will be like this.
Yeah.
So it will be 0. Under C2Y, all will flip. 1, 2 will come here. Here 1 and 2, 3, 4 will go there.
C.
So it will be 0. Same case with
X.
X,
0.
it will be 0. I, this will also be 0 because these will get changed, these two will get exchanged.
Yeah.
Now under sigma xy, xy is what? Molecular plane. So here nothing will happen, so it will be 4, and these two, they will reflect, so these two will be 0.
Sure.
Like this will be the reducible representations.
Yeah.
So when I break this, so when I say I'm breaking the reducible representation into irreducible, what I'm doing, I am using the D2H character table and the formula in the previous question.
Yes,
So
ma'am.
I will get this as AG B1G plus B2U plus B3U. So these four uh, representations I will get. Okay.
Yeah.
Now, in order to prepare the SALCs using these sigmas, SALC means symmetry adopted linear combination, and we make SALCs using the side atom. So here main atom, central atoms are what? These carbon, but SALCs we are making using the hydrogen orbitals, atomic orbitals. So
Yes.
this is SALC, symmetry adopted linear combination. So first, to generate the SALC, we are using the projection operator. Now projection operator, we need to find the linear combination of atomic orbitals which have the symmetry Ag or B1G or B2U or B3U. Okay,
Yes, ma'am.
so to do that, first let's figure out which linear combination of these sigmas have the symmetry Ag. So to do that, let's say I am working with Ag. So projection operator of Ag, and when it is applied on sigma 1. Okay, if you will do this with others, again also you will get the same answer, because these are equivalent. Sigma 1, sigma 2, sigma 3 and sigma 4 are equivalent.
Yes, ma'am.
Now how the projection operator applies on sigma 1? So what happens, it is Ag, right? And Ag means totally symmetric representation. So the characters under a this, I don't have D2H point group here. Let me find. Okay, so here we have D2H point group. Okay, so you see under Ag the characters are all one. Okay,
Yeah. Yes, ma'am.
this is totally symmetric representation. Okay, so I'm putting it on the side. So what we will multiply everything by 1. Now now first term will come due to the first symmetry operation, which is E. Let me write it like this, then it will be easy. The second term will come due to the symmetry operation C to Z plus 1 into, why I am multiplying 1 every time? I am
It
multiplying
is
these
single.
ones. Yes, I am
Yeah.
multiplying these characters. If it would have been -1, I would have written -1 here. Okay.
Yeah.
So where -1 will come? See, here is -1, right?
B1C.
So for B1G, the third term will be multiplied by -1. So this is important. We have to multiply by the character of the representation. Third term, Again I am multiplying with plus 1, but this will be for C2x, and then something will come here, okay, that I'll write later. This will be for I, this will be for sigma xy, this will be sigma xz, this will be sigma yz. Okay, so this is now sigma 1. Let me draw again here. So this is sigma 1, sorry, I draw pi, sigma 1, sigma 2, sigma 3, sigma 4. Okay, these
Yes, ma'am.
4. So from I'm drawing this thing again. Now first operation is E. Now what will happen when E applies on sigma 1?
Polar scale.
No, don't see the 4. We have applied the projection operator only on sigma 1. So just
Okay.
concentrate on sigma 1. What happens to sigma 1? Whether it remains same or it
Remains
changes.
same.
Yes, so it remains same. So
Yeah.
we have to write sigma 1 here.
Okay.
Now C2Z. Z was coming out of the plane.
Yes, ma'am.
So here we had C2Z out of the plane. So what will happen?
It will change.
It will change. It will change to what?
Sigma 3. Sigma
Um,
4.
sigma
4.
4.
4.
It will change to sigma 4.
Yeah.
So it will change to sigma 4. Next,
C2Y.
what will happen when you apply C to Y? So
It
Y will be this.
will,
This is X. This is Y.
sigma 1 becomes sigma 3.
Yes, it will become sigma 3. Then
C2.
C2X,
Sigma 1 becomes sigma 2.
sigma 2. Yes. Now under I,
Sigma 1 becomes sigma 4.
sigma 4, right? Under sigma XY,
Sigma 1.
yes, correct. Then sigma XZ.
Z.
So
It
XZ
passes.
is,
Sigma 1 to sigma 3.
no. So let me see.
Same.
Okay. XZ is, so this is
Sigma 1,
Z.
sigma 2.
This is Z. So this plane, a plane like this. So a
Yeah.
plane like this will be sigma XZ.
Yeah.
So it will be sigma 2.
Two.
Sigma 2. And then sigma YZ,
Y Z. Sigma 3.
sigma 3. Very good. So this will happen. So you see every term is coming twice. Sigma 1, sigma 1. Sigma 2, sigma 2. Sigma 3, sigma 3. Sigma 4, sigma 4. So when this projection operator AG is applied on sigma 1, we get 2 times sigma 1, sigma 2, sigma 3, sigma 4. So this only is asked in the question.
Yeah.
These coefficients do not matter. These coefficients are not normalization constant and they do not matter. Only what matters is the linear combination of these uh, atomic orbitals. So the question here was, a projection operator operates on sigma 1 and gives sigma 1, 2, 3 and 4. The projection operator is of symmetry species what?
AG.
AG. So we applied AG symmetry species to get this. So this is the correct answer. So we got, in this case, we got the correct answer only in the first attempt, because here
Yeah.
first symmetry, first representation was AG. So
Yes.
if the question, can you solve this if the question was like this? Mm, so let me, what to change? Okay, let me change like sigma 1 minus sigma 2 minus sigma 3 plus sigma 4. Which symmetry operation will give this linear combination?
Uh,
Now you have to try all three.
yeah.
AG we saw already. So
Yes.
AG gives totally symmetric, all the plus. Now you
Yes.
have to check all three and see which one gives this combination. Can you do
Sure.
that?
Yes, ma'am.
Can you do that now? Rishi?
Um,
Okay. Shall we try now?
yeah. Now, please show ma'am character table.
Okay, sure. So let me copy this and so I'll highlight what things you need to see. So we need B1G, this one, B2U, this one, and this one. These three.
Okay.
You have to multiply with the character. If negative 1 is there, you have to multiply by minus 1.
Yes, ma'am. Um, uh, got it, ma'am. 2 times sigma 1 minus sigma 2 minus sigma 3 plus sigma 4.
2 times, say again.
Sigma 1 minus sigma 2
Okay.
minus sigma 3 plus sigma 4
Right. For
in
which?
case of B1G. B1G.
B1.
B1G.
You got it in case of B1G. Okay.
Yes, ma'am.
Yes. Yes, it's correct. Hmm. So here also you got lucky because the first one was B1G.
Yes,
Okay.
ma'am.
So for B1G you will get twice sigma 1 minus sigma 2
Sigma 2
minus
minus
sigma 3.
C2.
Okay.
Yes,
This is
ma'am.
it. So So like this we solve this. Okay.
So,
So
yeah, ma'am.
for B2U also you will get something, and
Sure.
B3U also you will get some combination.
Yeah.
Okay. So this is it. So this is the third question. Okay. So now second question. So of the following, the statements pertaining to the use of a subgroup rather than a full group for complicated calculation. The correct one is complex characters are necessarily avoided, smaller number of projection operators required, group subgroup relationship is necessarily of many one type, all characters of the subgroup are +1. So here the question, we had a question regarding complete and incomplete projection operators, right? So
Yeah.
now the question is about group and subgroup. So for bigger molecules, first of all, we are using incomplete projection operator. Means we are only dealing with characters and not the whole transformation matrix. So we came one step down, less number of calculation. Now for bigger molecules, incomplete projection operators also, there are so many elements. So there are so many elements or operations in the uh, point group. Suppose for example, octahedral, there are how many symmetry operations for this?
Many.
48.
Yes, ma'am.
Okay, so you have to find, so what you did here, you found the, so you here 1 2 3 4 5 6 7 8, here you had 8 projection operator, but we took 15 minutes to solve this. So suppose
Yeah.
here we had 48 symmetry operations, so it will
Yeah.
take a much longer time,
Yes, ma'am.
and there are chances of making mistakes also, right?
Mm-hmm.
Because
Yes.
of plus minus and like that symbols. So for bigger molecules, what we do, we break it into smaller subgroup. So for octahedral, we look for subgroups like D4H, okay, C4V. So the subgroups, we do the calculation for subgroup and then extend it for the main group. So this is what it is, the question is about. So we use the subgroup rather than the full group. Okay. So what is the advantage of such a process? The advantage of such a process is only that the smaller number of projection operators are required. So the answer is B. So now here the number of, what is the order for D4H? 16. So for D groups, what you need to do, you need to multiply D and this order. So it will be 16. So suppose I am saying D3H. What is the order? So you need to multiply it with 4. So it will be 12. Okay. And so for
Okay.
C groups, you need to multiply it with 2 into the N. So it is 4. So here the order is, so for C4V, the order is 8. So suppose if I am using a bigger molecule whose order was 48, but if I can use a subgroup, then I need to work out only this 16, from 48 to 16. 16 projection operators, only 16 elements are there to work with. Okay, so this reduces the calculations, right?
Yes, ma'am.
Yes, so here the smaller number of projection operators are used, and now the calculations are very easier. So the correct answer is this one, B. Okay.
Yes, ma'am.
Yeah. Have you watched these lectures about projection operators and group subgroup?
Yes, ma'am. Yeah,
You
yeah.
watched?
Yes, ma'am.
Okay. 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 So now we come to the first question in the last.
Yeah.
So in a square planar complex given in this figure, so we have PTCl4 molecule, sigma 1 minus sigma 3 forms the basis for a two-dimensional representation along with what? So if you have watched the lecture, you can answer this. This exact question has been solved in class. So let's see. So for now we have sigma 1 here. So let me write like this. This is sigma 1. Okay, let me simplify it. Let me write like this. Sigma 1, sigma 2, sigma 3, sigma 4. Okay, this is a square planar complex. PT, in the center we have platinum and the Cl bonds across this line. Now when you will do this, to find the reducible representation of these four sigmas, so what you will get, what is the point group here?
D4H.
D4H. So for D4H, again we have E 2 times C4, C2Z 2 times C2, perpendicular C2, okay, perpendicular to C4. Now 2C2 dash, this is in between the bonds, 2S4, then we will have I, sigma H, sigma V, 2 sigma V, 2 sigma D. Okay, so we have these many operations. Now when you will, I'll give you the answer for this. Now the SALC will be, so we are considering the four atomic orbitals separately here. Under identity, nothing will happen, so all four will remain at their place with character 1 1 1 1. So the sum will be 4. Under C4, C4 axis is here. Under C4,
I'll
what
change.
all will change place, so it will be 0. Under C2, they will change place, it will be 0. Now C2, which is perpendicular, so means this C2, one this C2, one is this C2. Okay, so when this C2 will be applied, these two will stay at their place, these two will change place. So here the character will be 2.
Okay.
Okay, now this is C2 double dash, means this C2 in between the bond. If you are getting any doubt, you can ask. So
Sure.
if this is a C2, right? If we will
Yeah.
apply this C2, these two will flip, these two will flip. So nothing will remain at its place. So here the answer will be, the character will be 0.
Zero.
Under S4, S4 means first we need to apply C4.
Four.
So when we'll
Zero.
apply C4, all will change place. So
Yeah.
here also it will be 0.
Zero.
Under I, again it will be 0
Zero.
because they will change their places. Now sigma
Four.
H means 4 because sigma H is molecular plane. Now
Yeah.
C2, sigma V means which plane? Sigma V is along the bonds. Sigma
Yeah.
D is in between. So sigma
Two.
V means this plane, a plane like this,
Yeah.
or a plane like this. So
Two.
for sigma V, suppose I'm considering this plane, so 1 and 2 will remain at its place, 2 and 4 will reflect. Sorry, 1
Yeah.
and 3 will remain at its place, 2 and 4 will reflect each other. So
Second.
here
Two
2
now.
will remain at its place. Now
Yeah.
sigma D means this
Zero.
plane. Yes, sigma D is, let me choose some other color. Sigma D is a plane like this. So these two will change, these two will change, these two will change, right? So
Yeah.
here it will be 0. So this is a reducible representation. Now when you will change it to irreducible representation, then it will become, how do we change again?
Equation.
What?
Equation of A, AI.
Correct. AI formula, right? Yes.
Yeah.
Great orthogonality theorem formula, GOT formula. Okay.
Yeah.
So we get this. Now we need to work out the projection operator regarding these and this symmetry operation. Okay. So
Okay.
I will write for the first two, because we need actually two. In the question it is asked to work out the second one, sorry, the third one, EU. So when this A1G is applied on sigma 1 or any of them, we will get totally symmetric representation. So here you
Yeah.
will get 4 times this. Like in last question, we got 2 times
Yeah.
sigma 1, sigma 2, sigma 3, sigma 4, all plus sign. So here we will get 4 times
Yeah.
this. And when you will normalize it, so there are 4 orbitals, so it will be 1 over root 4, which is 1 over 2. So after normalization it will be 1 by 2. We ignore this term because this coefficient is not needed, so this will be 1, 2, 3 and 4. This is the SALC of E1G symmetry.
Yeah.
Okay, now we need to find, okay, similarly I'll tell you for B1U. Under B1U, so when you will apply the projection operator B1U on sigma 1, you will get sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. Okay,
Yeah.
1 over 2 normalization constant.
Sure.
How I am calculating these?
Just we have solved our previous question.
Yes, exactly. Just how I did in the previous question. I'm
Yeah.
multiplying with the characters of
Character.
B1U using the character table and checking how sigma 1 is getting transformed under all these operations, under E,
Yeah.
under C4,
Yeah.
C2, like this.
This one.
Okay. So next is under E. So when you will apply, here when we'll do this, we get this. We only get sigma 1 minus sigma 3. Okay?
Okay.
But E is a two-dimensional representation, so it should give 2 SALC.
Okay.
Okay, it is a two-dimensional representation, right?
Yeah.
So it should give 2 SALC, means 2 linear combination of atomic orbital, but here I am getting only one, this one. Suppose let me write it phi 3, this was phi 2, this was, oh, psi, I'm writing psi, I'm speaking phi. So this, so we need one more, which is psi 4. What is it? This we need to figure out. Okay, this is
Yeah.
the question. So the question is, sigma 1 and sigma 3 forms the basis of two-dimensional representation along with what? There should be one more linear combination of atomic orbitals which has the same symmetry EU, like this. Okay,
Yeah.
so the answer to this is sigma 4 is 1 over root 2 sigma 2 minus sigma 4. Okay. How do we get this? We get this using the character table again. So suppose we have a two-dimensional basis x and y, okay,
Yeah.
and the point group is C2V,
Yes.
okay.
Mm.
C2V doesn't have a two-dimensional representation. Uh, the point group, okay, let it be. So suppose when you will apply E, nothing will change. So x will remain x, y will remain y. If you'll apply C2, suppose x becomes y, y becomes x. Like this,
Yeah.
any of these two possibility will be there, or either nothing happens to them. So here
Yeah.
what is happening? Either they will get interchange, the basis will either get interchanged among themselves, or they will not change when symmetry operation is applied. Okay, so when something is when something forms a two-dimensional representation, C3, when something forms a two-dimensional representation, so when you will apply a symmetry operation on it, either x will remain x only, or it will change to y only. These two possibilities there. Okay,
Yeah.
so here we have sigma 1 minus sigma 3. This is a this is one of the bases of a two-dimensional representation, right?
Yeah.
One of the bases of a two-dimensional representation. Okay, so when I apply the symmetry operations of the point group D for H, what should happen? Either sigma 1 minus sigma 3 should remain sigma 1 minus sigma 3, or else it should give the other basis. Okay,
Yeah.
suppose
Ye-
suppose we know C3V is my point group, and I have two-dimensional representation some x, and this part we don't know. So what we will do, we will apply symmetry operations E, C3, okay, C2 and so on over x, and we will see to what basis it gets transformed. Under E it will remain x, under C2 it will have some combination of xy, under C3 it will have some combination of xy, under C2 it will become y. So we will get an idea, okay, that the second element here, the second element in the basis set should be y, because x is getting changed to y. Okay.
Yes, ma'am.
Okay. So similarly, in this case also, we have only one element of the basis, which is sigma 1 minus sigma 3. We have to find what is the other element. So that we will do by applying symmetry operations on this, and we will see to what basis it gets transformed. So let me explain you. You will get, when I apply E on sigma 1 minus sigma 3, it should, nothing will change, so it will be sigma 1 minus sigma 3. Okay. Now next is I'm applying the operations of D4H group only. Okay.
Yeah.
Now second operation is C4. So C4. When I apply C4 on sigma 1 minus sigma 3. Now you remember where is my sigma 1, sigma 3? This is sigma 1 and sigma 3 is sigma 4. So when I apply, this is sigma 1 minus sigma 3, this is the combination. Okay. When I
Yeah.
apply C4, what will happen? This will go here, this
Sigma
will come
1,
here.
yeah. Sigma 1 becomes sigma 2, and sigma 3 becomes sigma 4.
Yes, so it will be sigma 2 minus sigma 4, right?
Yeah.
Yes. So this is a new basis. This
Yeah.
can be our new basis, but we cannot be sure until we apply all the operations. So when
Yes.
you will apply next operation, which is C2, under C2, so you are applying C2. C2 is here itself.
Yeah.
So what will happen? In place of 1, sigma 3 will go, and in place of
Sigma
sigma
3.
3, sigma
Yeah.
1 will come.
Yes.
180
Sigma
degree.
3 minus sigma 1.
So sigma 3 minus sigma 1, and I can also write it as minus of sigma 1 minus
Minus
sigma
sigma
3.
3.
Okay. So here
Yes.
we can change the
Six.
here we can say that this basis did not change, it just changed its sign.
Yeah.
Okay, like plus 1 to minus 1. Okay, so
Yeah.
this is not a new basis, this is the same basis. Now suppose C2 double dash, sorry, C2 dash first. C2 dash sigma 1 minus sigma 3. Now C2 dash is, let me show you, C2 dash is this along the bond.
Yeah.
So what will happen? Nothing will get
Same.
changed.
Sigma 1 minus sigma 3.
Sigma 1 minus sigma 3. But when you apply C2 double dash, C2 double dash is uh, C2 double dash is like this in between the bond.
Okay.
So what will happen?
Sigma 1 becomes sigma 2.
Yes. So it will be sigma 2 minus sigma
4.
4. So now here we got a new basis again, which is sigma 2 minus sigma 4. So when you will apply the further operations, S4 when you will apply, so S4 you will get sigma 2 minus sigma 4. When you will apply I, you will get minus of
Sigma
sigma
1
1
minus sigma.
minus sigma 3, because they will change their places among themselves.
Yeah.
Okay. And when you will apply sigma h is what? Molecular plane. So when you will apply sigma h, it will be sigma 1 minus
Minus
sigma
sigma
3.
3.
Nothing will change.
Yes, ma'am.
Next is when you will apply sigma v. Sigma 1 minus sigma 3. This is 1, okay?
Yeah.
When you will apply sigma v. So sigma v is along the bond.
Yeah.
So nothing will change. So it will remain sigma 1 minus sigma 3. But when we'll apply sigma d is in between the bond, like C2 double dash. Sigma d is here. So these two will change, these two will change. Okay. So
Yeah.
it
Yes.
will give sigma 2 minus sigma 4.
Sigma 4.
So here you see, either we are getting sigma 1 minus sigma 3, or we are getting sigma 2 minus
2
sigma
minus
4.
sigma 4. Yes, ma'am.
Yes, so the other basis set should be sigma 2 minus sigma 4. Okay.
Yes, ma'am.
When you will do this other way around, like when you will do all these operations with sigma 2 minus sigma 4, Then also you will get sigma 2 minus sigma 4 or sigma 1 minus sigma 3, like this,
Yes,
same as this. Okay, so these two jointly form the basis under this symmetry operation, under EU.
yes,
Okay,
ma'am. Yeah,
using the projection operator thing, we are getting only one and not the other because these are degenerate.
yes, ma'am.
So the other one we need to find through this way. So the answering this question here, the answer should be this,
Sigma 2 minus sigma 4.
sigma 2 minus sigma 4. Not the plus combination, here not the plus combination, and these are 3. It cannot be 3. Okay,
Yes, ma'am.
so lastly I can write like sigma 1 minus sigma 3 and sigma 2 minus sigma 4. These two SLCs are of EU symmetry. Okay,
Yes, ma'am.
so in this molecule, first we had got, for A1G we had got this psi 1, 2, 3, 4, all totally symmetric.
Yeah,
For B1U we had got psi 2, 1, sigma 1 minus sigma 2 plus sigma 3 minus sigma 4. For EU, we have got sigma 1 minus sigma 3, which we call psi 3. So now we have got psi 4. So this is our psi 4. This is our psi 4, and you should normalize it like this. Okay. So here you see, here we had psi SLC was A1G, which is one dimensional, B1U, which is one dimensional, and E, which is two dimensional. So we should have got 4 SLC. So we got 4 SLC now, psi 1, psi 2, psi 3, and psi 4. So finally these
yes,
4 are the SLCs. Okay,
yeah,
okay, okay. So this was the first and last question.
yes,
Do you
ma'am.
have any doubt?
No,
This was
ma'am.
clear, right? How we
Yeah,
find? Okay, okay,
okay, ma'am.
okay. So if you have any question, you can ask. Otherwise, I'll close the session.
Now, what is the use of projection operator? Operator.
Okay, so we are using this projection operator to simplify. Otherwise, we have to find all the symmetry. So we have to find the SALCs for big molecules. The projection operator is useful. Otherwise, we will form, how we don't know how many linear combinations we can take, right? Suppose
Yeah,
if suppose a big molecule is there which has so many pendant atoms or the side atoms, 1 2 3 4 5 6 7 8. Okay, like this we have 8 pendant atoms. So 8 atoms you can arrange in how many ways? The plus and minus combinations for 8 atoms, it will be 2 to the power 8 combinations, right?
yeah,
So 1 plus, rest minus, 1 minus, rest plus. Like that, we can have so many combinations for each of them, right? So
yeah.
if we will do it manually, so what projection operator does is it simply gives the symmetry operation. Sorry, it directly gives the SLCs.
Okay.
So that's why we use it.
Sure. Thank you.
Yes. This is just to simplify the calculation.
Sure.
Okay. Anything else?
No, ma'am. Thank you.
Okay. Okay, so next week we will discuss the week 11, and after that week 12. One more class I will take.
Okay.